All right, good morning and afternoon, everyone, and welcome to the Sage Live of February 2025. Before we start, let me briefly explain what the Sage Journey is all about and how Sage Live fits in that journey. Sage Journey is a program whose mission is to inspire and encourage students to explore STEM careers for their future. We do this by offering free summer camps, paid internships, professional growth sessions, and many opportunities to connect with STEM professionals who care about you and your future. So Sage Live is part of the Sage Journey. It's an online gathering of students who have attended the summer camp and are curious about the next steps in their Sage journey. It's also a time to reconnect with the Sage volunteers, and there are a lot of them. It is held monthly via Zoom between the months of August and May. And the topics covered are relevant to your journey, whether it's career related, such as designing your life, resume workshops, how to prepare for an interview, or new and exciting topics such as quantum computing, AI, and machine learning. My name is Bernadette Uzzi from Brookhaven National Laboratory, and I oversee the K through 12 programs for the Office of Workforce Development and Science Education. I have a background in biology, but I was always fascinated with space and space exploration. I was 11 years old when NASA launched Voyager 1 and Voyager 2. Yes, I'm dating myself. But this event really sparked my interest and curiosity about the universe. And now, as an adult, I find myself working at a national laboratory where moon rocks from Apollo 11 were studied by our scientists, and more recently, instruments at our Center for Functional Nanomaterials and National Synchrotron Light Source 2 were used to analyze the chemical makeup of meteorite and asteroid samples. There's a NASA facility on our campus to study the effects of cosmic radiation in order to create better shielding for astronauts and electronics for long-term space missions. And engineers in our instrumentation division designed the CCD array that's found in the Rubin Observatory Legacy Survey of Space and Time, a very big telescope that is situated on the mountaintop in Chile. So I'm inspired every day by the work that is done at Brookhaven and across all the national labs. So I'm excited because today we have a guest speaker from Brookhaven National Lab who will talk about a new radio telescope project that will operate on the far side of the moon. The Lunar Surface Electromagnetics Experiment NIGHT project, or LuSee-Night for short, aims to detect radio waves from the universe's ancient past. Please welcome Connie Deane, a mechanical engineer at Brookhaven National Lab. She graduated from the University at Buffalo with a Bachelor of Science in Mechanical Engineering in 2020 and jumped right into research and development at Brookhaven. Connie also has a background in dance, dancing most of her life and continuing her studies in college to earn a Bachelor of Arts in Dance. Through her time at Brookhaven, she has worked on numerous scientific projects, including space initiatives like LuSee, and extending to quantum, environmental, and particle sciences. Today, Connie will talk about the LuSee-Night project and her journey to becoming a mechanical engineer.
Thank you so much, Bernadette, for that lovely introduction. And thank you, Sage, for hosting me today. I'll share my screen and we'll get started. So, yeah, that's a little bit about me. and I work here at the instrumentation department, which is under the Discovery Technologies Directorate at Brookhaven National Lab. And I've been here for almost 5 years. So, a couple of projects that are under my belt, and we'll talk about those things today. So a little bit more about myself is that I was born in Hanoi, Vietnam. I was adopted at 3 months old. My parents are in the chat, and I grew up in Rochester, New York, and I graduated in 2020 from the University at Buffalo. I graduated with both of my degrees at the same time, so I was pretty busy in college. It took me 5 years to complete both degrees, and I was going anywhere from like 18 to 21 credits per semester. and a couple summers here and there. So really busy student. And additionally, when I was at University at Buffalo, I started really kind of my career journey as a student assistant at the 3D printing lab, which was a new facility there. And there was this like, I was looking all over, scouring the internet for some opportunities at the colleges. And this one little link showed up. It was like looking for a student assistant at the lab, at this 3D printing lab. And I worked there for like about a year and a half. And that turned into an internship at Aurelia, which was local to me during the summer. And I interned there after my between my sophomore and junior year, and then my junior year and sophomore year. So I interned there twice. And then right after that, I graduated. I moved to Long Island and I worked at BNL. And so that's where I am today. And it's nice to talk about how I, got to be an engineer, but how did I know I wanted to be an engineer? I really didn't always know that. But I could tell that there were signs because I'm very tactile as somebody who dances and is in a physical space. You're always acutely aware of space and the space around you and the way that your body moves. And so I went into school at I'm like in sixth grade, and we were doing like CAD projects where we were building like little houses and stuff. And I thought that was really cool. And then we did bridge building contests, and those were things that really stood out to me in my middle school. That I was like, I really like this, and I was like, I'm not sure what I can do with it, but it seems really cool. And so I kind of brought that into high school when I accelerated my science classes and stuff. And when I got to physics in my junior year, I had this like connection because I was dancing a lot and I was just trying to be very aware of what was going on. And then physics happened, and we were doing these physics experiments with throwing balls, and you're bouncing things off walls and just kind of messing around with things and putting math to it. And that was really interesting to me. And I really enjoyed that. And it was my junior year of high school when my physics teacher said to me, he's like, you should be an engineer. And I was like, well, I don't know what that means. And I went into college. I said, I'm going to go for engineering. And so I signed up for biomedical engineering. Um, but I got to chemistry, and that was a little bit difficult for me. So I was like, I think I'm going to talk to my chair of the engineering department because I don't really know what engineering looks like outside of school. And if I'm struggling with chemistry now, maybe biomedical is not the route for me, because then I would have to go into organic chemistry, which was looking a little bit dire. So I went over there and I said, is mechanical engineering right for me? And he said, if when you graduate, you'll likely be applying to the same jobs as a biomedical engineer, because the types of engineering jobs that are out there are just so broad and vast, and there's so many different sectors that you can get into when it comes to mechanical engineering. He said if you don't know exactly what you want to do right now, mechanical engineering will open doors for you later. So I took that advice, and I continued to study that. So now I'm here at BNL after successfully graduating college. A little bit about BNL is that it was established in 1947. It's home to 7 Nobel Prizes. This picture to the right here is a picture that I took myself from the rooftop of the tallest building at BNL. And I think it's the absolute best viewpoint of the lab. And it's 5,300 acres of a campus, and that's some of the buildings here, but there's a lot of forest and nature and turkeys around here. We're like 60 miles east of New York City. That's about a train ride and a 20-minute car ride to New York City. There's an annual budget around $650 million a year, and that will support all of the people who come here, which includes our staff, which is about 2,500 people, and then 5,000 guests plus per year, and that probably includes some of you who come to the things that we host here at BNL. We have 6 directorates across the lab. There's 20 departments that range from biology, chemistry, computer science initiatives, EIC, which is a really big one, the electron ion collider, NSLS2, which is a light source, a lot of different departments, magnets, accelerators. It's all really good stuff. But as you can imagine, we can't all do all of that stuff. So what I do is I'm here at the instrumentation department. So I was wondering what I could say about the instrumentation department. And I went onto our website and it said we are creating customized solutions to instrumentation challenges, from detectors probing for fundamental particles created in the formation of the universe to quantum networks for the internet of the future. And I was like, well, that's really funny because I worked on both of these projects. So some of the projects are small detectors, like this little picture you can see on the right here. These are like 3 millimeter by 6 millimeter by 3 millimeter detectors. And this was going to be used to detect nuclear particles and gamma rays and all that stuff. And eventually this would be used to study astrophysical objects, and it could be sent on an instrument in the future. Additionally, I worked on the quantum network, which is a quantum network, but this is in the format of a free space link, which means that you're not sending quantum network through cables and wiring, which we mostly do, but you would be sending it by a laser. So you would have one point sending a laser and the other point receiving a laser. And that's why quantum is considered one of the safest forms of internet. So hard to kind of explain to some people what quantum internet is, but it's the safest form of internet because it comes from a sole source and it is received at a sole source, and there's no in between. So something like this, the free space, will be eventually used to connect the tallest building at Brookhaven to the tallest building at Stony Brook. And very exciting stuff. We're actually on the rooftop right now, and that picture I took earlier was from us installing the building and everything. So now we'll talk a little bit about LuSee. It's the Lunar Surface Electromagnetics Experiment at night. It's a collaboration between NASA through the Space Sciences Laboratory at Berkeley and through the Department of Energy with Brookhaven and Lawrence Berkeley National Lab, which is also known as LBNL. It's a Pathfinder radio telescope designed to investigate low-frequency radio astronomy from the lunar far side. And it is expected to launch in early 2026, so in about a year, if I'm correct. And it'll be on Firefly's Blue Ghost lander, which is really exciting. And this is so groundbreaking for research if this does come through. And so I'm gonna be asking, why are we sending a radio telescope to the far side of the moon? Well, this is to observe the dark ages. And to get to the far side, we want to go there because it's really quiet. And all the radio transmissions that we have from Earth, we have a lot of radio telescopes that already do exist. But you can imagine there's a lot of noise coming from Earth and all the things that we do here. And so the moon acts as its own sort of satellite and blocks all of that noise, and it's really quiet over there. So we started this project in 2023, and to launch it in 2026 is quite a feat because projects in the past for NASA and notoriously have been known to take a long time to be launched and to be landed. And for good reason, because you need time to develop really good science. But why is it so fast then? It is a challenge for the people who are working on it, but it is because the world is currently in a renewed race to the moon. So you've seen probably a couple things about Japan sent something to the moon, China sent something to the moon, Russia sent something to the moon, and they're also trying to get to the far side too. So the race to get there is so that we can get there before there's other instruments up there to create noise. So there seems to be a little bit of a period where we can launch this, and if we're successful, we could get hopefully a good year of some data if all things go well. And that will be great. The project is a technology project. So this commercial landing program that payload services, that's what it's called, by NASA, is a technology experiment. So we're testing the technology that we have, not necessarily a science experiment where we have expectations for results. Of course, that's a really, really good thing to have, and an additionally really important thing to have if you have all the data and everything. But really we're trying to launch, and we're trying to land, and we're also trying to test our instruments. So this is what these projects are made to do. And that's why we have so many of them launching. So here at Brookhaven, this was our challenge. It was if we look, I'll go back and kind of circle this. So this top gray box here with the antennas sticking out. This is the instrument box. The antennas are part of Space Sciences Laboratory. That's what they're responsible for. And then everything that's inside of the box that processes signals, and there's the electronics and a battery and senders and receivers. Those are all the things that Brookhaven is responsible for. So this is how collaboration kind of starts. And the gold one on the bottom is the lander, which is something that we're giving everything to them, and then they handle the rest from there. So this is what the inside of that gray box looks like. And the engineering challenge that I was faced was that there's a thermal challenge on the moon because we are in vacuum on the moon. So when you think of heat transfer, there's 3 ways to do heat transfer. And if you're looking at this pot with water, you'll see all 3 of them here. So conduction is the one where you put your hand on the handle and the heat is immediately transferred to your hand. Convection is the heating of particles like gas and water and all those things. Those particles move around and they heat each other. And then radiation is the one where you can feel the heat radiating off of that surface. So these are our 3 modes of heat transfer. But when we're on the moon, we don't have convection because we don't have air particles. So the only way that you can have heat transfer is through, yeah, I can go over why we're doing this research again. Sorry, I'll back up a little bit. So here is a graph of what researchers and physicists believe happened at the start of the universe. This is a timeline that tells you from the very beginning at the Big Bang. We have the Big Bang happen, and all of these particles expand, and there's a lot of noise in this area. There's a lot of microwaves. This is what they call the microwaves era. And I'm not exactly sure how exactly all of this stuff, because I'm not necessarily the physicist who can word this all correctly. But from what I can understand is that we don't really know a lot about the Dark Ages. It's a period in the Big Bang Theory that is not widely known because it's really hard to recreate the Dark Ages because we have so much light. I mean, we have all of this, everything is so much more mature now that having to go back into the Dark Ages is very difficult to observe, and especially here on Earth, and so there's a statute of limitation of the research that we can do. We know a lot more about galaxies and things because we have telescopes, and we have astronomers and physicists, and we have gamma ray detectors, and we have satellites and all of those things. We have Voyager. Those are all things that give us information about the universe, but we don't know a lot about the Dark Ages. That's what I can tell you. So the Dark Ages are tough to, I think radio telescope is the best way to be approaching this because there's no light, right? So you can't recreate something that doesn't have light. So the only way to be able to do studies on the Dark Ages is through radio, I would say. That may not be the most sophisticated way of saying that, but from what I can understand, this is a widely considered not very well known era in the Big Bang Theory. I don't know if that clears up anything in the chat, but you can definitely continue to ask me some more questions. The Dark Ages. I'm going to pull that up for you right now. I'm not too ashamed to say that I'm not going to just say something. It's So it's a period in the early universe where no stars or galaxies existed. So that means there's no visible light. It was very dense at this time. There was caused by a dense fog of neutral hydrogen gas that obscured any light sources. So that's what the Dark Ages are. And the Dark Ages lasted quite a long period, as you can tell on this scale here. But does that make sense? The Dark Ages, no light, very dense. All right, great. Okay, we will keep going. I'll talk a little bit more about this. So the challenge that we have on the moon is that we don't have all three modes of heat transfer. So we don't have any convection. So the only way that we can conduct heat is through conduction or through radiation. But the lunar surface is quite harsh, and that means that it gets really, really cold at the nighttime. It gets really, really warm in the day. And that's not the same as an Earth day, because an Earth day is like 12 hours and an Earth night is 12 hours, whereas a lunar night is 14 Earth days and a lunar day is 14 Earth days. So you can imagine having your electronics be at freezing cold temperature for 14 days can provide some challenges, as well as it being super hot. So all of the electronics that this instrument depends on do have a range that they have to be within. And so our challenge was to, how do we remove the heat from this during the day? And then how do we keep the heat inside at night? And so we use these things called thermal switches, which you'll see here on the right. And they are operated passively, which means that there's no electronics, there's no power that turns them on or off. Actually, it's built in within itself. So when it reaches a certain temperature, the material expands and connects, and that turns the switch on. And when that turns the switch on, it makes the box that's on the inside conductive to the outside of the box. So that might be a little bit more convoluted in what I'm saying right now, but basically when it's the thermal switch is off, it's very cold, and the material contracts and is away from each other like this. And so the heat from the inside will stay in. And so how are we observing the Dark Ages using this device if it was so long ago? So this brings up a really good question. Why would we be trying to observe something that has happened so long ago? The idea of this is that when we go to the far side of the moon, that's the closest area that we can get where we can see, where it's very dark. It's the darkest that we could possibly get to. It's never going to be the exact same as the Dark Ages. A lot of the things that we do in science to study the universe cannot be redone. We can't create the Big Bang again. We can't, but we try. That's why particle accelerators exist. That's why we're putting, $3 billion into a project over 10 years to create a collider that will expand on the research that's already being done. The reason why we would do this is because there are researchers that are interested in this internationally. This is not just something that, Brookhaven or even Space Sciences Laboratory said, hey, this would be a good thing to do. This studying the Dark Ages is known to be difficult to do because it is hard to recreate an area with no visible light, and to recreate the atmosphere of what space really looked like, because we can create a dark box possibly on Earth, but when you think about all the different particles and muons and all these things that physicists will talk about that are emitted from Earth at all times, we can't. It's much more difficult to create that space versus on here versus on the moon, because the moon is it's very new. Like it's is I'm trying to, because we as humans and life on Earth have created so many things on Earth, right? And the moon is almost like it's like looking back into time because it's untouched. The moon has nothing on it really. I mean, on the grand scheme of things, we have a couple of things that are on the moon, but on the grand scheme of things, the moon is mostly untouched. So going up there and performing science experiments on the moon is a way of being as close to natural science and the natural space that we can get. Does that make sense? Okay, good. Okay. So this was our mechanical challenge for Brookhaven. And so my task was to do some thermal testing and validation. And as an engineer, you're going to be, how do I approach this? So the first thing that you do is you define your requirements. I was given a design. This is a base plate that is cut out as much as it possibly could be, but still be structurally supportive for the large things that we put on there, like a battery that's like 40 pounds. So the thing with space too and launching things is you want them to be as light as possible. So we want them to be as light as possible. We also want them to be as thermally efficient as we can get. And so you'll know your design, you'll know how much heat you're putting into the system, and you'll know what the acceptable temperature range for the things that you're putting your system through. The second thing you'll do is you'll do some thermal simulations, some hand calculations. You'll validate your design through computational analysis, and then you'll bring it to the real world. So that's the cycle of what testing as an engineer is, whether that's for space or whether that's for industry or other places in general. There's a typical way of approaching things, and this would be a simple way of putting it. So my challenge for the thermal testing was that I don't have a vacuum chamber that's big enough to hold this huge mechanical instrument. So what I had to do was try and recreate what vacuum would be like, but in Earth and with the air all around us. So what we do and what I did was create artificially create the thermal sources from the inside, and then also artificially create vacuum by insulating and trying to cover up all of these surfaces to try and keep it from being influenced by any convection. So this is how it looked at a certain point. It was very fun to kind of just put tape on everything and be like, oh, this is a space instrument. Because at the end of the day, you're like, oh, when people joke around and say engineering is duct tape, and you're like, I think that's true. And so this is what I mean by artificially creating heat. So I would be putting a silicon heater sticker on this board. Now this board is not populated with any electronics because we were not going to be able to have the full system ready because there were other engineers, electrical engineers, who were working on a board design in tandem. So sort of like what we were talking about before, like you can't always recreate the dark ages, you can't recreate the Big Bang, but what we can do in science is do our best to try and recreate to what we do know and what we have available to us. So that's what I did here. So I put a heater on this board and I put some thermocouples, which are little sensors that will be attached to a data logger, and you'll be able to read what temperatures are changing in real time. And that's how I approached this. We did end up putting it into, more foam insulation and a big foam box, and it got to be quite the monster. Now, some additional tasks that I did. Thermal testing was a big one for me because I had never done it before, and I had to really kind of do a little bit more research on heat transfer. I did that in college. I had taken that class in college, but when you get to, benchtop testing for space projects, there are a couple more things that you have to think about, and it was really nice to be able to revisit some of my, my college homeworks and literature, and it was very exciting. Additionally, we have never worked on space projects before. Brookhaven is not how this is our first real collaboration with NASA, especially on a space project where it's being launched and our name is going to be on it and everything. So we have a new facility. We needed to have a clean room because when you have space, hardware, it has to be very, very clean because if it's not very clean, you have oils and you have metals and you have things that also create their own magnetic field. And when you put those into space or you launch those, they can interfere with the electronics and they will short out electronics. And so they have to be very clean. It has to be inspected thoroughly. There has to be gold plating on everything. It's a really different way of approaching how you have to build things because most of the times we're just like, we'll just put a screw here and a little nut and bolt here, and that'll be that. But there's a little bit more thinking to do. So we had to create a whole new facility. And so what I did was I needed to make clean room procedures. I needed to make sure people were trained on how to use a clean room. And I also needed to make sure we had all the material for clean rooms. That means like hair nets and lab coats and booty covers and masks for everybody. You have to have wipes and gloves, and you have to have a specific amount of alcohol, like isopropyl alcohol, to clean surfaces. And then outside of that, I had to create some more systems. Like, how do we clean hardware? How do we store that hardware and document where it is, so that way when we send it to somebody, we know where everything was. We have taken pictures of everything. We have evidence of sending things over. And so I did that as well. So cleaning, storing, documenting, shipping, space hardware. And then I did some 3D printing so we could check the assembly before everything was fabricated. So these are all things that a mechanical engineer can do and would possibly do. It's not always just design work. Design work is great. I do a lot of design work. But there's additional things that need to be done. Like sometimes you'll look at a production floor and you'll say, people are getting injured on when they build this over and over. What can I do to change the design to make it more efficient so the people who are assembling it don't get hurt? Sometimes those are the things that engineers do. And so these are some of the pictures that I took throughout the process. And my favorite one here is during the cleaning process, where everything is A-OK, because I really needed to know that sometimes. You can see down here, this is a 3D printing one. To the left of that is the shipping container and taking pictures of that. I did epoxy some parts together. This top right corner picture with that's kind of close up. That's how I was inspecting things. I had a little UV light, and I was in the lab with my UV goggles on, and I had a little magnet on there, and all the lights were off, and you look to see if there'd be any purple fluorescent sort of dustings on it and stuff like that. And then to the right of that is the clean room, and then down there is me and my clean room girl aesthetic, and some gold plated parts, which are so beautiful to look at. They're so gold and bright. And so these are the highlights of the project, and I'm definitely excited about this project, and I'm excited to see that it is where it is, because we have successfully completed it on the BNL side. We finished it within the budget, within the time frame, and it's been highly praised at the lab. So now they're at SSL, and they're going to be assembling everything together and then getting ready to send it over to the lander, to Firefly at some point this year. And my latest project is going to be creating what we are calling a cloud in a box. So I can't show you exactly what it's going to look like, but I did complete my design, but it'll be a cloud in a box, that is for sure. And I'm just leading the mechanical effort on that now. It's a $200,000 project. I'm designing it. I'm sourcing all the material for it. I'm writing all the procurements, and then I'll be writing all the assembly work and helping my team assemble it. So those are the types of things that I do, and I'm looking forward to doing. And thank you. And I know we have Bernadette here to maybe talk a little bit more about the education programs that we do have, but I figured I would just leave this link here for you guys, to check out all the things we have going on. It's nice, this page, you can set it up, you can click on the different grades and stuff, so you see which ones apply to you. But thank you so much for having me, and let me know if you have any questions.
Thank you, Connie. It's just what an amazing experience the LuSee-Night project must have been for you because it, that's the first thing that you started working on when you joined Brookhaven. Is that true 5 years ago?
Actually, no, I actually started working on that in 2023. So all the things that I was saying about basically starting the thermal testing and then going all the way from shipping our hardware, that was probably a year. So I was busy that year. um, there was a lot of, back and forth with people because you're working on it for a year, but things change. And so it's a lot of fun to be on top of such an exciting project. And things are always moving when you have something like that. And you realize that there's a lot of important science and other people's jobs that are also working on this. At the end, there will be a certain amount of names that are attached to this project, and a lot of them will be the scientific staff and the people who led this project. But for the amount of people who have actually put their hands on this project or been in meetings about this project or even just signed off procurements on this project, I mean, we're talking about hundreds of people who've been involved in this process, and everybody has been a joy to work with because this project really is so exciting.
Well, it's true that science is so collaborative, and it's not just you're collaborating with somebody that's in your department, but it's someone on the other side of the world or, the other side of the country in this case, right?
Mhm.
Have you physically gotten together with the folks at Berkeley? Like, have you traveled there or have they come to Brookhaven?
Yeah. I had a chance to when the project was first starting up, and we were talking about the thermal. That was the biggest hang up on this project was how are we going to handle things thermally. So I went over to JPL, which is over in Pasadena, um, and the jet propulsion laboratory, and this guy was presenting his research on it kind of looked like a box inside of a box. His instrument was creating like 4 watts of heat, and he needed to have that self-contained. And so what he did was have this box be extended by cables to an outside box, and that's how it was thermally isolating it. And he was trying to propose that to us to use that for our research, but we are creating like 80 watts of heat, so we didn't need to isolate it like that. But it was really cool to go over to JPL and talk to him about his research and sit in the big meeting room, and also go to the hangar bay and see the instrument for Europa being built in the hangar bay. It was really exciting, and yeah, it was one of my highlights of my career for sure.
Um, I don't know if you can, if you have an answer to this, but is there a chance that you'll be able to go to the launch? Um,
I'm really hoping. The thing that I really, because they'll have a launch date. Things like this kind of get like, okay, there's a date, but then it's like, the cloud was in the wrong place today. We have to wait until tomorrow. So things like that can kind of happen. But I'm hoping to take off some time to go down there and at least see it, get ready to be launched, even if I don't see it launch right away. But it would be really cool to see it. Absolutely.
at a minimum, we should have a watch party.
Oh, for sure. Oh,
Yeah.
for sure. Absolutely.
I just want to remind everybody that's on the Zoom call, feel free to unmute yourselves or, pop a question in the chat. We did receive some questions via email, and something uh, for your profession, for mechanical engineering. What kind of math is most useful for you?
Hmm. Honestly, I don't do a lot of stress testing I mean, the thermal testing I did was a lot of the math that I most recently did, but a lot of it is more like GD&T, tolerancing parts and doing tolerance stack ups and putting together assemblies and making sure that when things are built, they will all fit together. And um, I guess that's probably not the right answer for everybody because I know there are some mechanical engineers who do a lot more math than I do. And they spend probably a lot more time doing simulation work or computational data work or um, computational fluid dynamics is a big thing at the lab now with these big, huge detectors. We have these really big detectors, and they're being pushed in with a little bit of heat, or I mean, a lot of bit of heat and a little bit of air, and they need to see how their system can handle that thermally. And a lot of that is done in uh, like a program nowadays, but you still have to have a very good numerical understanding of what's going on so you can diagnose your simulation work, because uh, it's easy to say, oh, we'll just put it in a program and forget about it, but there's a person behind there, and there's brains behind what those numbers mean. And so somebody not like me might have more understanding of the math that's needed to do something like that, but every position is different. That's what I'll say.
Um, so um, mentorship, do you, I don't know, in college or, at the laboratory, do you have some person or a few people that you would go to that support you in your learning process and, the projects that you're working on?
Mhm. Yeah, I have a mechanical engineer manager who does help me out with projects and offers me assistance and guidance on a lot of new things that I'm working on. And sometimes how do I approach this, down to what is the material and the math that I need to know, because there are things like stress testing for nuts and bolts, for example. A lot of that is, you have like a machine handbook, and you'll have an equation that you're trying to solve, and you'll be like, as long as the stress is underneath this on this nut or this bolt, then it should be safe. And what factor of safety is that? And so I'll have somebody to help me kind of work through those problems and understanding and honing in on what I really need to focus on. um, but I will say I'm sort of in a unique situation at the lab, because I work on smaller projects as sort of like the sole mechanical engineer. So a lot of things I have been doing or have been working on, I do a lot of research myself, and spend a lot of time reading through articles or looking through the BNL's library, or looking through different literature and articles and books, uh, just to see. A lot of the stuff that I'm working on is novel, like novel instruments that have never been done before. So I have to kind of look out there and see, is this something that I can do? And is this something that's been done before? And spend a lot of time um, doing a lot of research, that's for sure.
Um, a question came in and they're curious about your job. So, you have a lot of different projects and like you just said, things, it's brand new,
Mhm,
right? It's never been
mhm.
done before. Do you find it tiring? Like your day to day, is it tiring or is it um, difficult but enjoyably challenging?
Yeah, there's definitely some days that are more challenging than others. When it comes to projects like NASA, or having big collaborative projects where these big partnerships are looking for results on a time basis, sometimes you're spending extra hours getting those results to them on time, and that's a part of the job, because we're working towards something. We also are collaborating with people, and they're depending on the things that we're doing. So having that in mind sometimes can be a little bit stressful, because you know that it's not just the work that you're doing depends on it, but it's the work that the whole team is doing depends on the work that you're doing. But in that way, it seems everybody sort of comes together in times like that too, and at least we're all there to support each other during those stressful times. But then there's times that are not so stressful, and where maybe work is a little bit slower, and maybe all you're doing is procurements or writing statements of work or sourcing material online, and it's not as stressful, but it's still productive work. uh, it does vary. I won't say that it is either always tiring or it's either not, and there's a little bit of a balance between that for me. But I do know that there's other people who work here at the lab as mechanical engineers who are like field engineers, who are always on their feet, who are always at different facilities, and sometimes they're on call. So it depends on where you're working. It depends what your role really is, because mine is sort of like building, developing, designing. Some people are on the field, and they're fixing things and they're repairing things, and they're um, um, assessing a situation and trying to navigate what are the different things that what the problem could possibly be. So um, I think everybody's job looks a little bit different, but it is something that I do enjoy doing, and having, the challenge presents itself. It's an opportunity. That's the way that I see it.
Um, so you do dance, right, outside of work. Um, is there anything that you do outside of dancing and outside of work that, you know, sorry, I'm having some activity in my house. I know Danielle mentioned it earlier. I have some too, so if you hear a noise, ignore it. Um, but I know that you do some science outreach.
Yeah.
I don't know if you
So
want to share
outside
that.
of, I don't really, to be honest, I don't actually dance as much as I used to. Um, and that's somewhat of a proximity thing, because I thought you're not as close to New York City as you want to be when you want to dance. It takes some time to get there. But I still like to stay active. I think that has ignited something different for me. I like to go on runs, and like the lab does a couple of like a 5K every year, and I like to sort of run with all my friends at work and everything. So my active life is a little bit more social now too, because it's sort of like getting together with people at the lab who are interested in the same things. And then outreach, I'm doing this STEM program at the Shinnecock Nation with my friend Kayla, who's also at the lab. She's an electrical engineer, and we've been going there for over a year now, and we've been going and bringing different STEM projects and materials to kids every Thursday for an hour. It's all we really get. And it's all we really need, because they're little. They're like 5 to 6. And at some point we had like 5 to 6 to like 10 to 11. So the age range was really big. And it'd be kind of funny because we'd have like to split up the activities and everything. But we've done so many things with them. We've done like volcanoes. I've done some Tinkercad with them. We started 3D printing their nameplates, and we had them design their own mug. Uh, we've done bridge building, squishy circuits. We did the marble racing. Thank you. Bernadette has been wonderful and offered me some material. And so we did marble racing. We did wind turbines. The kids really loved those. That was a lot of fun. They've never touched like a screwdriver before, or like they don't know all those. So it was really cool to have them assemble this wind kit together and bring it outside to the to the park and watch their things. Their LEDs light up and the wind turbines going. Um, we've done some bacteria was fun. That was that was a good one, because we had the kids put their hands right on that bacteria, and we came back a week later and we said, oh, look how gross these are. And you're like, yep, you better wash your hands. And that was fun. We've done so many good things. It's been really cool to be out with the kids. It's a highlight of my week, because um sometimes engineering is mundane. It's not always stressful, but sometimes it is just kind of like, I'm just designing some things today. I got to put screw holes in this certain pattern, or I have to, analyze this simulation. And so it's not always glamorous, but bringing something new and exciting to kids, and having like this young energy, and like even if it's sometimes silly, where they're like don't totally get it, it's just fun to see the kids get involved in something new. And we've done solar system stuff with them. Yeah, and I love that.
Well, you said glamorous, so there is something glamorous about wearing a clean room suit.
Yeah, it's quite the fashion statement, especially when you forget that you're wearing your booties, and you're wearing your booties like around your shoes all day long.
Um,
I see a, and
yeah, I
I'm
see
not
a
sure if
question in the chat. about summer programs and how to be more involved. So there is the SAGE Consortium is made up of 8 of the national laboratories, and each one of those hosts a summer camp. Depending on the laboratory, there are day camps, like for a week, and some offer residential camps. That's a good segue. Connie, I don't know if you had any closing remarks or any, final thoughts before we close.
I will say that if you're looking to get involved and you're not close to a lab, or go to your library, go to your local library and see what they're doing, see what kind of things they have going on. Some libraries have 3D printers, but not sometimes the staff doesn't know how to use them. And so they wait for people to come there and, print things, or, they don't. So sometimes there's resources in your local community that you can pull on, or you can add to. You can add to those resources. The things that we're doing at Shinnecock are things that mostly you can just buy from the dollar store. You can look up STEM activities for kids. If you just want to try and run a day like a program for like a day or something, and be like, I think if you want to get involved, libraries are a great place to look, or your school. Your schools can have those clubs too. I know my school had like an automotive club and stuff like that. But definitely using Sage Journey as a resource is great resource. And I think as many resources as you possibly can use, but don't be afraid to get involved. Yeah.
Thank you. And I see Daniela put the link in the chat to more information about the summer camps. So, Connie, thank you so much for sharing your journey and a little bit about the projects that you're working on in the lab. And yeah, I think you have a fan club. So we're looking forward to LuSee-Night and the other projects that you're on.
Yeah, absolutely.
And I'd just like to thank all the students and the volunteers that have joined us this morning. So I think we'll be, yeah, Connie, you can take down your,
Okay.
yep. And
And
then,
thank you guys. Thank you so much for having me.
yeah, you're welcome. All right, so please follow Sage on social media at Sage S Camp. Sage Live is one Saturday a month, the same time as today. The next Sage Live Camp, Sage Live event is Saturday, March 8th, where you will hear about medical isotope research and production at the National Labs. And the Sage contact information for anyone that has questions is info@mysagejourney.org. Thanks, everyone. Have a wonderful weekend.